In this video, we will analyze rational functions such as these, looking for the vertical asymptotes, the horizontal asymptotes, and maybe even the holes, if there are any, and we'll state the domain. So looking at number 1, the numerator is not factorable, but the denominator is. So let's go ahead and factor the denominator. This would be x plus 2 times x minus 2. Now, the vertical asymptotes come from setting the denominator equal to 0. So looking at the x plus 2, that would give me a vertical asymptote of x equals negative 2. Looking at the x minus 2, that would give me a vertical asymptote of x equals positive 2. Okay, horizontal asymptotes come from the end behavior. So let's ask ourselves, what would happen to the function as x gets bigger and bigger and bigger? Well, the negative 2 and the negative 4 would become insignificant as x gets bigger and bigger. So the function will approach x squared over x squared, which equals 1. That means that the horizontal asymptote is going to be y equals 1. Horizontal lines are always y equals a number. Okay, now for the domain will strictly come from vertical asymptotes and holes, if there are any. So I can really just look at the vertical asymptote. I don't need a graph. I can tell that the domain is going to be from negative infinity to negative 2, union negative 2 to positive 2, union positive 2 to infinity. All right, I'm just putting a break where the two vertical asymptotes are. Okay, looking at problem number 2. Okay, so the vertical asymptotes are going to come from setting the denominator equal to 0. So if I do that, I'm going to get x equals negative 4. So that's my vertical asymptote. Now, this numerator is factorable, so I feel like I should do that just in case it will cancel out with the x plus 4. This is the difference of two cubes. So if I were to factor this, the difference of two cubes factors as a binomial and a trinomial. So the binomial will be x minus 2. And then I'd have x squared plus 8x plus 4. All right, but the x minus 2 and the x plus 4, nothing canceled out, so there are no holes. Okay, and in fact, so with that in mind, I don't really need to worry about the factorization. Anyway, horizontal asymptotes. The horizontal asymptotes will happen based on the end behavior. So function h, as x gets bigger and bigger, the negative 8 and the plus 4 will become insignificant. So I will have x to the third power over x. But that simplifies down to x squared. Well, as x gets bigger and bigger, this expression will just simply approach infinity. So since that is not a constant, like 0 or 2, that means there are no horizontal asymptotes. So the domain. For the domain, I'm really just looking at this vertical asymptote. So to the left of the vertical asymptote, that's negative infinity to negative 4, union. And then to the right of the vertical asymptote, that's negative 4 to infinity. All right, so that's it for number 2. All right, this one, they nicely factored it for us, so that's very helpful. The vertical asymptotes come from setting the denominator equal to 0. Okay, so this is going to be vertical asymptote of x equals negative 3. and x equals 4. All right, I can tell there will be no holes because nothing is going to cancel out. So I should be able to say the domain right now. Okay, because there's a vertical asymptote at -3 and there's one at 4. So the domain is going to be in 3 parts. It's going to be from -infinity to -3. All right, there's my first asymptote. And then it'll be between the asymptotes, so union -3 to 4. And then it will continue after the asymptote, so that'll be from 4 to infinity. So there's the domain. Now, the horizontal asymptote is going to come from the end behavior. So as x gets bigger and bigger, what will happen to this function? Well, the -1 and the 2 and the 3 and the -4, those will become insignificant. So the numerator will approach, that's going to be x to the 4th power. X times x squared, that's x to the 4th power. And the denominator will become x squared. This will reduce down to x squared. Well, as x gets bigger and bigger, this is just going to approach infinity. So since this is not a constant, that means there are no horizontal asymptotes. All right, glancing at number 4, the vertical asymptotes will come from the denominator, setting the denominator equal to 0. So that'll be x equals -3 and x equals -5. Since there are no holes, all right, nothing cancels out, I can say the domain right now. It's going to be from -infinity to -3, all right, there's the first asymptote, union, and then it will be, you know what, I messed that up a little bit because on a number line, -5 comes first, right? Like we have -5 and then -3 would be to the right. So I better say -infinity to -5 union -5 to -3, all right? That's like between the two. And then union -3 to infinity. Okay, so got to be careful about the order of things there. Now, the horizontal asymptote is based on the end behavior. So what happens to function g as x gets bigger and bigger? Well, the -6 and the 3 and the 5 will become insignificant. So this function will approach x over x squared. This simplifies down to 1 over x. Now, as x gets bigger and bigger, this is going to approach 0. Think about it, as x is getting bigger and bigger, you have like 1 over 10, 1 over 100, 1 over 1,000, 1 over 1,000,000. The fraction's getting smaller and smaller as the denominator gets bigger and bigger. It's getting closer and closer to 0. So that's why the horizontal asymptote is y equals 0. All right, number 5, let's factor. Looking at the denominator, there's a GCF, so this will be x times x plus 2. In the numerator, maybe this will factor. 2x squared will factor as 2x and x. 1 can only factor as 1 times 1. I don't think this is factorable. All right, so you know what? This is not going to factor. But that's okay, because I don't need the numerator. In order to know the vertical asymptotes, I just have to set the denominator equal to 0. So from the x, that's going to give me x equals 0. From the x plus 2, that's going to give me x equals -2. Okay, so that means that the domain is going to be, now I got to be careful because as far as the order goes, on a number line, it goes -2 first and then 0. So be careful with your domain. So it's going to be -infinity to -2, all right, because that's the one you get to first. union, and then negative 2 to 0, okay, as we go between the asymptotes, union 0 to infinity. That's the domain. Okay, for the horizontal asymptotes, we analyze the end behavior. So what happens to h of x as x gets bigger and bigger and bigger? Well, in the numerator, only the 2x squared is going to matter because the smaller degree terms will become insignificant. In the denominator, the 2x is going to become insignificant. So this function will approach 2x squared over x squared. The x squared will cancel each other out, so that equals 2. So that's a constant, so that's a horizontal asymptote at y equals 2. All right, looking at problem number 6, the vertical asymptotes come from the denominator, so that's going to be x equals -1, x is equal to 3. So nothing cancels out, so there are no holes. So the domain is going to be negative infinity to -1, union, -1 to 3, union 3 to infinity. I checked real quick to make sure that these were in order from left to right. Now, the horizontal asymptotes come from the end behavior. So as x gets bigger and bigger, the -4 and the 2 and the 1 and the -3 will become insignificant. So this is going to approach x squared over x squared, which equals 1. So that means that the horizontal asymptote is y equals 1. All right, again, the vertical asymptotes come from the denominator. So I'm going to have x equals -4 and x equals 5. All right, those are my vertical asymptotes. My horizontal asymptotes will come from the end behavior. So as x gets bigger and bigger, all right, the 2 and the -3 and the 4 and the -5 will become insignificant. So the function will approach x squared over x squared, which equals 1. So the horizontal asymptote is y equals 1. Now the intercepts. So this means the x-intercept and the y-intercept. Well, you can get the y-intercept by substituting 0 for all the x's. So if I put in 0 for all the x's, okay, that's going to leave us with 2 times -3, so that's -6. 4 times -5, so that's -20. So that's going to be 3 over 10. Okay, so the y-intercept will be 0, 3 over 10. Now, for the x-intercept, you set the numerator equal to 0. All right, so if I set the numerator equal to 0, that's going to give me x equals -2 and x equals 3. But intercepts are ordered pairs. So that -2 is really -2, 0. And that 3 is really 3, 0. Okay, so those are the intercepts. All right, number 8. Vertical asymptotes come from setting the denominator equal to 0. So that will give me x equals -2 and x equals 1. All right, the horizontal asymptotes come from the end behavior. So as x gets bigger and bigger, the 3 and the -6 and the 2 and the -1 will become insignificant. So that's going to approach 2x squared over x squared. But those will cancel each other out, so that'll give me 2. So the horizontal asymptote is y equals 2. Now, for the intercepts, that's the x-intercept and the y-intercept. You can get the y-intercept by plugging in 0 for the x's. So if I put in 0 here, and here, and here, and here, that's going to leave me with 3 times negative 6, so that's negative 18, over negative, whoops, I put 16, negative 18 over negative 2, which is 9. So that's the y-intercept is going to be 0, 9. Now, the x-intercepts come from setting the numerator equal to 0. All right, if I set this equal to 0, it's going to give me, okay, I will have negative 3 over 2 from the first factor, and I'll have x equals positive 6 from the second factor. So that's going to give me negative 3 over 2 comma 0 and 6 comma 0. All right, number 9. The vertical asymptotes come from setting the denominator equal to 0. So that's going to give me x is equal to 2 and x is equal to negative 2. All right, the horizontal asymptote comes from the end behavior. So what happens to h of x as x gets bigger and bigger? Well, the negative 2 and the positive 2 will quickly become insignificant. So that's going to give me 8 over x squared. As the x gets bigger and bigger, this is going to approach 0. All right? If you have a larger and larger denominator, the fraction is getting smaller and smaller. So horizontal asymptote is y equals 0. Now for the intercepts. You get the y-intercept by letting x equal 0. So if I put a 0 here and here, that's going to leave me with 8 over negative 4, which equals negative 2. So that means that the y-intercept is 0, negative 2. Now the x-intercepts come from setting the numerator equal to 0, but in the numerator I just have 8. 8 can't equal 0. That means there are no x-intercepts. So again, the vertical asymptotes are going to come from the denominator. If I set these equal to 0, that's going to give me x equals negative 5 and x equals 6. So those are my two vertical asymptotes. The horizontal asymptotes will be the end behavior of this function. So what happens to h of x as x approaches infinity? Well, the 2 and the 5 and the other 5 and the 6, the negative 6, those will become irrelevant. So that's going to leave me with x squared. And here I have x squared times x, so that's x to the third power. This would reduce down to 1 over x. Now, as x gets bigger and bigger, this fraction will get smaller and smaller. So it's approaching 0. So that's why the horizontal asymptote is y equals 0. Okay, now for the intercepts, I can get the y-intercept by letting all the x values be 0. So if these are all 0, then in the numerator, that's going to give me 10. In the denominator, well, 5 squared, so that's 25 times 6. I don't know what that is. All right, 25. Is it 150 maybe? Okay. So that's 150. So that's going to be negative 1/15. So that's the y-intercept right there is going to be 0, negative 1/15. Okay, but what about the x-intercepts? Well, the x-intercepts come from setting the numerator equal to 0. Okay, so the x-intercepts, well, you know what, let me slow down. I have to be careful of one thing. See how we have an x plus 5 in the numerator, and we actually have two x plus 5s in the denominator, because it's x plus 5 squared. So let me just spell it out for a second. Now, these two x plus 5s will cancel each other out. So there's actually a hole in this graph because of that. But when it comes to the x-intercepts, this x plus 5 won't be around anymore. It's going to cancel out and be a hole. So no x-intercept. So the only remaining intercept comes from the x plus 2. So that's going to give me x equals negative 2. So which makes the x-intercept be negative 2, 0. Okay, problem number 11. I feel like this denominator will factor. So if it can, we need to do that. So x plus 1, x plus 3. Okay, so nothing cancels out, so that's something to watch out for. Okay, so the vertical asymptotes are going to come by setting the denominator equal to 0. So that's going to be x equals negative 1 and x equals negative 3. The horizontal asymptote comes from the end behavior. So what happens to g of x as x approaches infinity? Well, the 5 and the negative 2 will become irrelevant. So in the numerator, that's going to give me x to the 4th power. In the denominator, the lower degree terms will become irrelevant. So that's just going to leave me with x squared. So this simplifies down to x squared. And as x gets bigger and bigger, this is just going to approach infinity, which means that there is no horizontal asymptote. So I'm just going to put none. Okay, that just leaves me with the intercepts. If I let all of the x values equal 0, that will give me the y-intercept. All right, but this 0 out in the front is going to make the entire numerator equal 0. And then I'll have 0 here and here. So that would be 0 over 3, which is 0. So that means the x and y-intercept will be 0, 0. Now, in addition to that, we might have more x-intercepts. The x-intercepts come from setting the numerator equal to 0. And if we set the numerator equal to 0, I'm going to get 0 from the x squared. If I set x squared equal to 0, I'm going to get 0. So that's where the 0, 0 comes from. Okay, if I set x minus 2 equal to 0, I'm going to get positive 2. So that's an x-intercept of 2, 0. And from the x plus 5, I'm going to get negative 5. So that's negative 5, 0. So those are the three intercepts. Okay. Number 12 and 13 are a little bit different. A rational function has x-intercepts at 0 and 4, vertical asymptotes at 1 and 6, and a horizontal asymptote at y equals 0. We need to make up a rational function that satisfies those criteria. So the x-intercepts come from the numerator. So I will get a 0 x-intercept if I have a factor of x. All right, so this 0 is going to lead to an x. Now, technically, these are not x-intercepts. These are technically zeros. So I should change my wording. If they just give me a number, not an ordered pair, technically those are zeros. So I'm just going to cross this out and write zeros. Anyway, the x-intercept of 4, 0 is going to come from a factor of x minus 4. Okay, so that's, my numerator has to have those two factors in it. Now, the vertical asymptotes come from the denominator. A vertical asymptote of x equals 1 would come from a factor of x minus 1. A vertical asymptote of x equals 6 would come from a factor of x minus 6. So this function that I just wrote, all right, I will call it f of x, all right, it's very original, then that would satisfy the criteria of having an x-intercept at 0 and an x-intercept at 4. And it would have the correct vertical asymptotes. So how about the horizontal asymptote? So I need to look at that to see if I need to modify this. The way it is, as x gets bigger and bigger, this function will approach x squared over x squared. All right? As it is right now, that's what would happen. Because the negative 4 would become irrelevant, and the minus 1 would become irrelevant, and the negative 6 would become irrelevant. So that would just leave me with x squared over x squared. But that equals 1, not 0. Okay, so if I want to end up with 0, I need more x's in the denominator. So for example, say if I had x to the 3rd power in the denominator, okay, then that would give me 1 over x. And then this would approach 0, which would give me a horizontal asymptote of 0. So I need the degree of the denominator to be higher. So I can do that by just squaring one of these. It doesn't matter which one I square. So for example, I could square this one, x minus 1 squared. Because I have not introduced any new factors, then there's no, it won't change the vertical asymptotes. I will still have these two vertical asymptotes. But this will give me x squared over x cubed, which will approach 0. Okay, so this is one answer to the question. There are many, many answers, right, other than this one. I could have squared the x minus 6 instead of squaring the x minus 1, for example. I guess technically I could have multiplied by a completely new factor, like x plus 3. That would give me another vertical asymptote that wasn't mentioned, but it didn't say that it only had these vertical asymptotes, so maybe there's a third vertical asymptote that we didn't talk about. But something like this would be the best answer to the question. Okay, let's try the next one. Okay. We need zeros at 2 and negative 3. Okay, we're talking about x-intercepts, basically. So a 0 of 2 means a factor of x minus 2 in the numerator. A 0 of negative 3 means a factor of x plus 3 in the numerator. So that satisfies those two. Vertical asymptote x equals 4 means a factor of x minus 4 in the denominator. Okay, now there's supposed to be a point discontinuity at negative 5 comma 0. I think that means a removable discontinuity. Okay, I think that's what they mean by point discontinuity. So that would be a hole. So that means I need x plus 5 and x plus 5. Okay, because these cancel each other out, that's what will give you a hole. That will give me a hole at -5 comma something. So this is pretty good. I'm just not sure about the comma 0 part. That's the only part that throws me off. Let's see what happens. If I do -5, okay, if I do -5, then that's going to be -5. And look, I'm looking at the part of the function that's left after I cancel these out. That would be -5 minus 2 times -5 plus 3 over -5 minus 4. So what does this make? Well, it's not going to make 0 for sure. This is going to make -7 times -2 over -9. So this is going to make 14 over 9. So -14 over 9. So this is going to give me a removable discontinuity at -5 comma -14 over 9. So that's close, but not quite. So how can I modify this so that I can get a 0 instead of -14 over 9? Well, here's what's necessary. I need an extra x plus 5 in the numerator. I need an extra one. So if I go ahead and square this, now I have 2x plus 5s. So it's really like having x plus 5 times x plus 5. Okay, if I write x plus 5 squared. This way, I still have the removable discontinuity at -5 because these two still cancel out, which is a hole. However, because I have this x plus 5, this extra x plus 5, then after I plug that in, you know, in order to find the y value that goes with the -5, I have these 3 factors in the numerator. So I have -5 minus 2, I have -5 plus 3, but now because of the extra x plus 5, I have -5 plus 5. That's the key. And then in the denominator, I have -5 minus 4. Now what really matters is this guy right here, because -5 plus 5 is 0. So if I get a big old 0 right here, and 0 times anything is 0. So I don't even have to sit here and calculate out the rest of this. The numerator is going to be 0. Okay. And unless this is 0, then I'm going to get 0. In this case, it's 0 over -9, which is 0. So that gives me the value, the removable discontinuity at -5 comma 0. So back to my actual answer, and I'm going to go back to writing it a little bit more neatly, more compactly, so I can put x plus 5 squared. So this would be a great answer to question number 13. Alright guys, that's going to do it for this video. Go ahead and click here in the red apple to watch the next video. Click in the green apple to subscribe, or click the yellow apple for the full playlist.